Okay, so now what we'll do is just look at how experimentally these energy levels were actually observed in atoms. And so before we actually go into the details, it's worth just defining a few techniques here. So the first term that we should know is this idea of just spectroscopy in general. So spectroscopy is a very broad term, and it refers to the study of the interaction of electromagnetic radiation with matter. So one form of spectroscopy is called emission spectroscopy, and so it's most helpful to look at exactly what's happening there. So the word emission kind of tells you that you're looking at radiation that's being emitted from an object, right? And so I have here kind of a schematic of how that might work. So let's say you had a sample that was emitting light, then what you would be doing is your sample would be emitting light. That light would hit something called a detector, which would count how much light is being emitted. And then that would turn it into an output that looks like this. And it would say, oh, I detected at some kind of either color or wavelength or whatever you're plotting against some emission. So in this case, it says there's emitted light at this specific kind of orange color. So in the opposite of emission spectroscopy is absorption spectroscopy. And so in that case, what's happening instead is that we're taking kind of generically white light, and what white light means is kind of all wavelengths of light, and we are shining that at a sample, and then what we're looking for is what does the sample kind of absorb and what does it not absorb, right? And so looking at the schematic again, white light comes into the sample, some of the light goes through the sample and then hits your detector, and then what you get as an output looks something like this, where you see all of the light that goes through the sample, but then a dark spot where the light got absorbed by the sample, right? And so again, these are in the end kind of telling you similar ideas, and just two different ways to figure out exactly what wavelengths of light are interacting with the sample. And so it turns out historically, what people really studied at first was the emission of atoms. And so here are some examples of experimental atomic emission spectra. And so just showing you a few different atoms, and what should really stand out to you right away is that each atom emits light at very specific kind of lines, specific colors, right? And that each of these atoms or elements has a distinct kind of a signature, right? So if you see a certain pattern of lines, that's going to correspond to only one element or one atom. At first, these lines were kind of just a intellectual curiosity, right? It's just interesting that there are lines and that they're kind of nicely spaced out. But as people thought about it more, so in 1885, Balmer realized that there seemed to be more than just kind of nice lines, right? There seemed to be a pattern that was emerging here, and he derived this equation. So this is entirely an empirical equation. Like he kind of just made equations until one of them made lines like the ones that they were seeing for the hydrogen atom, right? And so what he determined was that at frequencies you could calculate for hydrogen based on this formula right here. And if you kind of plug all of this in, you will find all the different frequencies at which you see a line. And that's kind of a first hint that this n value shows up, and this n is an integer, right? So that means that there are discrete values that make sense for plotting emission lines. The next level was taken by Bohr, and he kind of realized and proposed that, well, if we're seeing these discrete emission lines, maybe there should be a model for the atom in which the hydrogen atom is absorbing light, and that light specifically is resulting in a transition between energy levels, right? And that these energy levels are quantized. And just going a little bit into the math here, then he defined the idea as being that the frequency might be equal to the ratio of the difference between those two energies of the two levels you're transitioning between, and Planck's constant here, right? And in other words, what that equation says is that your delta E, your difference in energy between two levels, is equal to Planck's constant times frequency. Cool. And so that's a great idea and a great proposal that Bohr had, right? That there are not only clearly lines that are emitted from atoms, but also that the explanation for those lines is that those lines correspond to the difference in energy between energy levels of the atom, right? So again, those lines are telling us that delta E value. That was the Bohr kind of model or hypothesis. And so whenever there's a hypothesis, you need an experiment, right? And so it turns out that the Frank-Hertz experiment provided some evidence for this model. And so I'm going to show you kind of what this looks like here. And so the experimental setup was to have kind of a nice tube here. So I'm showing that in gray, a tube. And in this tube, there were kind of mercury atoms just in vapor form. So just kind of mercury floating around inside this tube. That was the idea. And kind of as a further step, the idea was that on one end of the tube, there was a source of electrons. So electrons would kind of be emitted from the left side of the tube as I've drawn it. And they would be detected at the right side of the tube. Right? And so what they were really looking for is, well, what do the electrons do as they're flowing through a tube like this? Right? And so in this top scenario, what they did is they controlled the energy of the electron source to be less than kind of a hypothetical voltage threshold. So just some voltage level. They didn't really know ahead of time, but they just kind of increased their energy to get to that level. So when it's below this threshold voltage, what you see is that all those electrons just go straight through. They don't do anything with those mercury atoms that are floating around. They just go straight through. So you see, X amount of electrons are being emitted at the source. You detect that many electrons at the detector. And so kind of a qualitative statement is that you detect current. And the other thing that you can see is that if you look at the emission coming out of the tube, so if you just looked at the tube and looked for any light coming out, you wouldn't see anything. And so that would kind of indicate your, let's say, I'm going to put the line right there. Right? So you're not seeing any color at all. There's no emission at all. It's just dark. Right? So in the second case, what they did is they kept changing the energy of those electrons that were coming out. Right? So I'll put another detector here. And so what they found is that as you increase the energy, you would hit a point where now those electrons are no longer detected at the detector. So once those electrons have enough energy, it's kind of weird because you would expect things with more energy to go through quicker, but that's not true. What you see, in fact, is that at that threshold energy, or the threshold voltage, those electrons disappear from the perspective of the detector. And in other words, if in the experiment there's nothing else except mercury around, that means those mercury atoms are absorbing the energy of those electrons. Right? And so again, no current was detected, but interestingly enough, you see an emission from those mercury atoms. Right? And so that would be kind of this purple color. I'll put my little arrow there. And so this was really kind of hard evidence that there might be these energy gaps, right? Once these electrons have enough energy that match the energy between two energy levels, then it's possible for that energy to kind of promote that transition related to the emission. It turns out that then you could kind of take the data from this experiment and plot it, and what you find, actually it works really nicely, is that the frequency of emission observed from the mercury turns out to be equal to kind of charge of electron times the threshold voltage divided by Planck's constant, which is exactly where we were before, right? Delta E equals h nu. Okay, so the point of all this is to just make the argument experimentally for Bohr's model, right? This idea again that there are, first off, atoms with discrete kind of emissions, and that in the Bohr model, or the Bohr kind of idea, the emissions correspond to transitions between energy levels. And all of this was first evidenced by this Frank Hertz experiment. Okay, now that we have experimental evidence for the Bohr model, or kind of the first experimental ideas for Bohr to think of his model, let's go through the math that Bohr did to explain the atom. And so Bohr's approach started from the planetary model that Rutherford had come up with originally, which is the idea that there's a nucleus and an electron, and those are separated by some distance r. And then kind of taking the total energy of the system, where that's going to be your potential energy and your kinetic energy together there, and then pulling from Newton's second law, which says that force is equal to mass times acceleration. And it turns out that for circular motion, as you might have in an electron orbiting a nucleus, then you would apply an acceleration that's actually defined as speed squared over that radius r. From all of that, then what you can figure out is that your Coulomb force is equal to the mass of the electron times the speed squared over r. Right? So based on that, Bohr's main idea was that, you can have these equations, that's great, but not all values of R or energy E are allowed. So only some of those values are allowed, this kind of quantization idea, right? Bohr's second idea was kind of a step further, which was that in addition to the value of R and E being quantized, then actually this idea of the angular momentum of the electron is also quantized. So we're not getting into the physics of exactly what all that means, but the best way I think about this is that, if you have something on a string, like a ball on a string, and you're swinging around, there's kind of an angular momentum that's pulling on that ball in a certain direction that's not completely circular, right? There's some forces kind of perpendicular to the actual rotation. And so anyway, based on those two ideas, Bohr did a little bit of math. So he started off by taking angular momentum, and so that's the equation. We're not deriving any of this ourselves, just kind of seeing the process that was gone through. So if the momentum L is equal to mass times velocity times distance, then you can actually figure out that that's, after plugging some things in, equal to nh over 2 pi. And once you solve all of that for your velocity, then you get to this jumble of equations, which then means also that the radius you can set equal to that jumble of letters, right? So if you don't believe me, you can definitely go through and do all the substitution math. What I've done here is I've left the various parts of these equations in different colors just to show you where they pull from, right? So some of that is from up here, and some of that is down here. Put together gives you this equation. And then finally, what Bohr did was to say, well, there's a bunch of constants in this equation, so let me pull all of those out here, right, and set that equal in the end to this kind of a naught. So that's the Bohr radius. So all of those constants kind of multiply and divide out. Turns out that total equals 0.529 angstroms, and that's a value that's called the Bohr radius. And so this is a nice, neat equation that he came up with, which was that, again, kind of that each electron has a specified distance from the nucleus of r that depends on an integer value of n, and it depends in a way such that for an equation, or for any atom, it should be n squared divided by z, atomic charge, times this Bohr radius. Okay, so that was R being quantized. So then you got to turn R into energy being quantized. So if we start off again with our equation for energy from our classical physics approach, then all of this mess turns into that mess right there. So again, kind of not showing you exactly how it's done, but it's pulling from the previous slide, some of those equations, and plugging things in. And in the end, what you find is that, again, you can essentially turn a bunch of that into constants. So all the things in orange here just simplify down to this constant times z squared over n squared, where again, n would be your integer value. So really, that's all there is to the equation. For a long time, people thought it'd be easier to just simplify this even further and to just not worry about that constant even. And so the idea was to think in terms of kind of units called Rydbergs, where in the end, for your Rydberg energy, that would just be defined as your z squared over n squared. And this would just essentially be given in units of Rydbergs, which are equivalent to that constant right there. Okay, now that we have the math figured out for the Bohr model, we should check it against some of the other experimentally observed properties of atoms that exist. Right? So we'll start off by looking at ionization energy. And so if you're thinking about ionization energy, in the Bohr model, ionization energy would refer to a process where your electron is kind of at the lowest energy level, so the n is equal to 1, it's the lowest possible energy. And then as that electron is getting removed from the atom, it's going to the highest possible energy value, right? So n is going to be equal to infinity. Right? Another way you can think about this is that n is close to the atom, n equals 1. Then as the electron gets farther away from the atom, n equals infinity. And so that means if we think about an ionization energy, then we can think about the electron ionization energy is when the electron is totally removed, right? So then that difference in energy from E at infinity to E at 1 should be similar to ionization energy. And so we can plug all of that in for the hydrogen atom here. And so if it's hydrogen atom, Z is going to be equal to 1. And infinity squared is very big. And Z is equal to 1 here. So this is kind of negative 1 times your negative 2.18 times 10 to the negative 18 joules. And that, of course, should be trivial math, but that comes out to positive 2.18 times 10 to the negative 18 joules per atom. And let's convert that into kilojoules per mole, just because that's kind of a more typical way that chemists think. So instead of one atom, we'll think about a mole of atoms. And so then that's going to come out to 1,300 kilojoules per mole. And so if you look at the experimental data for hydrogen and the first ionization energy, what you get is pretty close. So you get 13 kilojoules per mole. Actually very close, surprisingly close, I'd say. Okay, now that we've compared the Bohr model, the math of the Bohr model against ionization energy, let's go back and compare against the original motivator for this Bohr math, which is the emission spectra for atoms. And so just recall that when you're dealing with light absorption and emission to an atom, or really to a molecule or anything else, you're dealing with actually transitions between energy levels of whatever it is that's absorbing or emitting light. And so again, that means that you have this delta E is going to be equal to h nu. That's kind of just one of these equations we should try to know. Or expressed more expanded out, that's going to be your final energy of whatever it is that you're dealing with minus the initial energy of whatever you're dealing with, and that's going to be equal to h nu. So if we plug that in, or plug the Bohr model into delta E equation here, this is what you get. I've simplified a little because I've already pulled out the terms that are the same between the E final and the E initial. And so that's most of this junk right here. You'll notice the z squared gets pulled out, but the n squared gets left behind because that's what's changing, right? The energy level is going from one number nf to another number ni. Another important note is that this is for emission, but we could do similar math for absorption. Once you have that, you can get to frequency for light just by dividing both sides by Planck's constant. And you get all of this stuff, and then where the orange kind of equals out to this constant here. Cool. So that seems great. How does that work out with the actual experiment? Well, so here is that emission spectrum for hydrogen, just for us to look at. And so what we're trying to do is to say, given an energy level diagram, so I have an atom, hydrogen atom, and I know that I have n equals 1, n equals 2, n equals 3, n equals 4, etc. What are the energy gaps there, and do they correspond to the wavelength of light or not, right? And so it turns out to work out really nicely. If you do all of the math and you compare against the experimental data, you see lines exactly where you're supposed to. You see energy differences and transitions exactly where they're supposed to be. Everything kind of matches between the emission spectrum and the Bohr derivation. And yeah, so just to give you an idea of what all of this means. So again, I've shown you here the emission spectrum where you see purple, blue, teal, and red. It turns out that people were really interested in kind of classifying all of these systems or these transitions out. So there's a lot of different names for all these different transitions, and they're categorized into series. And the series are categorized by the endpoint, so kind of the final energy level that you're at. So the Lyman series is always looking at the transition that ends at energy level n equals 1. Turns out that those are too high of an energy for us to see. That means they're at too short of a wavelength for our eyes to see. So they're all kind of in the ultraviolet or higher energy regimes. The ones that we do see in the emission spectra are from the Balmer series. And so I've shown you just a few of these, but it turns out that for the blue line that you see here in the emission spectrum, that blue line comes from n equals 5 going down to n equals 2. While the teal line you see is because the atom is going from n equals 4 energy level down to n equals 2. and then the red emission is from the n equals 3 energy level down to n equals 2. And this should match our intuition in that the smaller the energy gap, well, the less energy that transition is, and the less energy involved in a transition, that means the longer the wavelength is for the light of that transition. The longer the wavelength is, the more kind of red in color it is. Cool, so that's great, right? A really great model, right? It feels like this should just work. If it works so perfectly for hydrogen, then, what's to stop it from working for everything else? Turns out, if you just go ahead and try for everything else, it doesn't work. And the Bohr model turns out to only actually be useful if you're dealing with a one electron system. Right? So that means you've ruled out essentially all of the systems other than hydrogen atom. And so to try to further understand these systems beyond kind of Bohr's understanding, we got to turn to some other models and approximations.